Hello everyone. Before starting the lesson, try the warm-up. What type of function are these? There's 3 different functions pictured here. See if you can remember how to tell what kind of function this is based on a table of values. So pause the video and try this on your own. For each function, I tried the first differences. If the first differences are constant, this is a linear function. If they're not constant, it's not linear. Next, try the second differences. If the second differences are constant, it's a quadratic function. If not, try the ratios between the first differences. So I just want to back up here. I'm not showing my second differences here, but they would be plus 4, plus 2, plus 1. The second differences are not equal. So try the ratios between your first differences. From one to the next, I'm multiplying by a half, or dividing by 2, or times 0.5. Either way you look at it, you're multiplying by the same number every time. That's an exponential function. So in this lesson, we're going to look at properties of exponential functions. By the end of the lesson, you'll be able to determine the characteristics of the graphs and equations of exponential functions. Now, we covered this in the warm-up, but just to reiterate, linear functions have constant first differences. Quadratic functions have first differences related by addition, which means the second differences are constant. And exponential functions have first differences related by multiplication. That's the ratios between the first differences. So if you get that idea, then the rest will make sense. Because in an exponential function I'm multiplying by the same number over and over and over again, we can simplify that down to an exponent. So this is why the exponential parent function is this: b, some number, to the exponent x. X is the number of times you're multiplying the base by itself. Now, it's an exponent because, remember, the ratios are constant. We're multiplying by the same number every time. Now, I put a b here because b can be any real number. The parent function could be this, it could be this, or it could be this. They'll all look a little bit different, but when we apply transformations to a function, we have to see what is the base of the power. That tells us what the parent function is. So let's look at a graph of f of x equals b to the x when b is greater than 1. Okay, so b is a number greater than 1. It could be 2, 3, 4, 5, off to infinity, or it could even be 1.00001. As long as it's bigger than 1, we will get a graph that looks something like this. Think about it. If b is, say, 2, for example, when x is 0, 2 to the 0 is 1. When x is 1, 2 to the 1 is 2, so it gets higher. When x is 3, 2 to the 3 is 8. It gets higher. As x increases to the right on the graph, then your y value increases as well. Let's work backwards. If b is 2, when x is negative 1, 2 to the negative 1 is 1 over 2 to the 1, which is 1 over 2. When x is negative 2, that's 1 over 4, etc. When x gets more and more negative, the value of our function gets smaller and smaller and smaller. Never actually reaches 0, though. So when we talk about the domain or the range of this parent function for any value of b greater than 1, we get a graph that looks like this. X can be any real number. X is an element of the real numbers. There's no restrictions. X can be any number here, and you will get an answer. The range, however, y can be any real number with this restriction. Y is greater than 0. There's no value of x that I can put into this function that will get me an answer of 0. Because any number raised to any exponent will never get an answer of 0. unless b is 0, but it's not. B is greater than 1. Notice I'm not writing y is greater than or equal to 0, like this. I'm not writing it this way because y cannot equal 0. You will never reach a value of y equals 0. So don't write it like this, write it like this. Y is any number greater than 0, not 0 though. In fact, that line, y equals 0, is called an asymptote. That's a word that means it's the line that never gets crossed by this function. This function will never touch the line y equals 0. It'll get closer and closer and closer to it, but never actually touch it. That's called an asymptote. The equation of the asymptote is y equals 0 for this parent function. Now, what would be the y-intercept of this function? Remember, on the y-axis, the value of x is 0. So when x is 0, doesn't matter what this number is, raised to an exponent of 0, what's the answer? Think back to your exponent rules. Any number with an exponent of 0 is equal to 1. So the y-intercept, when x is 0, y is 1. Doesn't matter what the value of the base is, the y-intercept will be 1. Now, the shape of this graph, is this exponential growth or exponential decay? Well, as you look at the graph from left to right, as x increases, what happens to y? It also increases. So this is exponential growth. So if the base of your power is greater than 1, you will have exponential growth, so your graph will look like this. You will have an asymptote of y equals 0, which means your graph will never touch that line, y equals 0. And your y-intercept will be 1. Now, what if b is not greater than 1? What if it's like 0.5 or 0.887 or 3/4 or some other number that's less than 1? Well, we can do the same process to figure out what a graph would look like if the base of the power in that function is between 0 and 1, meaning any fraction less than 1. Let's pick 0.5 just as an example. What will the graph look like as x gets bigger and bigger and bigger? Well, when x is 1, 0.5 to the exponent 1 is 0.5. But when x is 2, 0.5 to the exponent 2 means 0.5 times 0.5, which is 0.25. It's getting smaller. So as you increase the value of x, the value of your function will get smaller and smaller. So you can see the graph is going the other way than it was when b was bigger than 1. Now we can go through and talk about the rest of this. The domain and the range remain the same as they were. X can be anything, but y must be greater than 0. The asymptote is y equals 0. That's the line that never gets crossed. The y-intercept will still be 1, because any number, even if it's a small number with an exponent of 0, gets an answer of 1. And because our function is getting smaller and smaller and smaller as x increases, this is an exponential decay. So the takeaway from this is to just watch out when you're looking at your exponential function. You got to think about what is the base of the power. If it's a value greater than 1, this is going to be exponential growth. And if it's a value less than 1, still positive though, you're going to get exponential decay. The y-intercept is always going to be the same, and the asymptote is always going to be the same. So it's really just noticing whether it's growth or decay based on the value of the base of your power. Now you'll notice in the previous slide, I had b is greater than 1 or b is less than 1, but what about when b is equal to 1? Why can't b be equal to 1? Well, think about it. If b was 1, you'd have the function 1 to the x. Now, it doesn't matter what x is. If x is 0, the function is equal to 1. If x is 1, 1 to the exponent 1 is 1. If x is 2, 1 to the exponent 2 is 1. You're always going to get an answer of 1. So if your function is always equal to 1, this is a straight line on the graph. Just so you can visualize, if we had an x and y axis here, this would be your function. That's not an exponential function. It doesn't grow or decay. It just stays the same value. So that's a linear function. So when I talk about the base of your power being either less than 1 or greater than 1, it's never going to equal 1 because that would make it a linear function. Now the practice for this lesson is fairly straightforward. You're just going to be looking at a table of values to find if it's linear, quadratic, or an exponential function, and also just identifying what type of function is represented by a graph, whether it's linear, quadratic, exponential, and what type of exponential, growth or decay. So as long as you know those things, you should be able to do the practice questions, but if you need help, just reach out.